I have been a long time developer of pipelines, but recently joined the Beam team here at Google, or the team primarily responsible for Beam, to kind of put my money where my mouth is after complaining about the infrastructure for so many years. So I thought I would talk about how and why I made that decision. I'm going to take the headphones off. It's just too distracting. So if you have questions, please put stuff in the chat. I won't be able to hear on the headphones for a little while I'm talking. So to kind of understand how I ended up here, I thought maybe I should go through kind of my personal history of big data processing and the things related to it, so that we can kind of see if we learned any lessons along the way and things that we might apply to Beam as I join the team as someone who works to develop the next generation of Beam. So when dinosaurs roamed the earth, I've been doing this for a while. I used to work a lot on sort of traditional high performance computing. So-called big irons. So that's large supercomputer installations with esoteric hardware construction, and then got into Beowulf Clusters, which was sort of the predecessor to what Google does. When this was before Google was founded, and these were the idea here is you used fairly cheap commodity machines to build things that kind of behaved like supercomputers. They weren't as good, but they were also a lot less expensive, and so it started to make large-scale compute accessible to areas that hadn't been traditionally used for large-scale compute capacity. In my case, it was bioinformatics applications. So when I was just starting out, the Human Genome Project was a thing, and for example, one of the clusters I worked on was for a biology lab that was looking for something called single nucleotide polymorphisms. So these are small single letter changes in the genome that have phenotypic effect. So in that world, it was very different than what we have today in a lot of ways. There were no orchestration systems. There was no airflow or anything like that. There were these queuing systems that came across from the big iron side. So DQS was one, PBS was another. They're still around today. They're still used today in HPC. But they basically assumed that you were doing a single large job that might run for days, weeks, or months on a bunch of machines. And other than starting up the job, it was basically their equivalent of an automated SSH. That's basically what they were. They would log into a machine, start a job, and then that was it. That's all the support you had. Disk was expensive, so you had these very expensive network-attached storage. So none of your work was local, so it didn't really matter where you ran anything. If you were especially lucky, you had some sort of fancy network for your network-attached storage that everything else didn't use. Sometimes that was files, but that also was true of sort of data warehousing applications at the time as well, right? You had some large relational database, typically Oracle, that ran on some special box somewhere that was very, very expensive, and you queried that, and then you used the little bit of data that came across to do your final processing, and then maybe you stored it to local disk. A lot of times you would materialize to your local disk, as much local disk as you had. Now your iPhone has 10 times the storage of one of these machines, because things were unreliable and you wanted to pick up work. But there was no support at the application level for doing anything. You had to basically roll everything by hand. But it was interesting because the storage was remote, because storage was so expensive that you had to centralize it in one location. And from there, that kind of went on for a while. It was like that for a number of years, and then in the mid 2000s, like 2008, if I remember correctly, this weird new project came out, Hadoop. I had left academia, and I was working at a company at the time, and on actually sort of like credit card fraud modeling and stuff like that. And this like weird new project came along that said, hey, you can take like logs and not have to worry so much about processing logs anymore. And it was a lot faster out of Yahoo, based on this paper that Google had written. And I, when I was finishing grad school, I remember, seeing the Sawzall paper. Rob Pike came by our department and talked about it once, and actually used that with it. So it's like, oh, I'll try, give this a shot, because we were still processing logs largely the same way we had been doing the big data processing thing, right? Like we copied the logs to various servers and did some processing maybe locally on that server, and then we uploaded to some MySQL database somewhere. So we gave that a shot, and that was like a revelation, right? Because it let us do a couple of different things. So one, it let us get rid of, or at least minimize the use of, one of the most expensive things in our hardware infrastructure at the time, which was these expensive either database boxes or network attached storage or something like that, right? There were a couple of companies that did that provided these pieces of hardware, and they knew it. But Hadoop, more so than the processing model, it brought along HDFS, right? Like that was actually a really big win for Hadoop. And what that did was let us split our file storage across many different machines. Disks were still pretty expensive and not so huge. So it let us get, an aggregate storage across lots of machines. Now, of course, you pay the cost, right? Because Hadoop, HDFS stores more than one copy of every block and things like that. But you were already paying that cost in a RAID system anyway, right? Like you big network attached storage also made copies. Hadoop was a little less efficient because it didn't use that fancy like read solvent stuff. Although there was nothing stopping you from doing that. I think actually Google was did. I don't know what the paper said. I don't know what it does. But that was a huge revelation. So now we could like just have huge stores of logs, and more importantly, it turned out those multiple copies were actually an advantage because we could parallelize our compute over the same storage more easily. The logs were both broken up into little pieces, and then if the machine that had one copy of the log was busy, we could run another job on the other copy on a different machine and do them both at once, which is something we couldn't really have done before. And also, we started to get some help in building out our log processing. So before, at this company and companies before it, log processing scripts were usually not great pieces of software. A lot of times they were written in, stuff like Perl, PHP at this particular company, and they were basically just fancy shell scripts, right? Like you didn't get any metrics out. You maybe knew if they completed it or not, but there wasn't a lot of support there. And so, Hadoop started bringing in, by simplifying the processing model, right, to the macro and the reducer, it started to bring in some support for automating, what had been a manual process of shell scripts and cron jobs and stuff like that. But the main kind of effect was really that we got this like moving compute to the storage and a computation. And then something kind of weird happened. So we were like, yeah, this is great. This is way more efficient. But then something kind of weird happened, and the cloud came along. And the cloud was odd because we had just spent all this time moving our compute to the data, and then we moved the data away again. Right? We started using things like S3 and GCS and whatever Azure calls theirs, and the storage wasn't local anymore because it was now cheaper to store it there, and we didn't have to worry about moving it around, and we didn't have to worry about maintaining. Most importantly, we didn't have to worry about maintaining the infrastructure of HDFS. At the early days, like nobody knew how to maintain this. So it's not like we had SRE and operations people to help us out. Like it was mostly folks like me, like data science teams. I was more on the data science side at the time. learning how to do ops, basically, learning how to be SREs and doing things like hand edit, discovering that the Hadoop secondary name node is very poorly named. It is in fact the very important name node and not the secondary name node. And the other thing that the cloud era kind of brought along was related to that operational change. The fact that now it was a lot easier to run a lot of different pieces of technology. Before, we tended to run a fairly small number of things, one type of database, one Hadoop cluster, because adding a new type of database meant you had to learn how to operate that thing and how to run it. And so it was a very, you had to hire people to do that sort of stuff. It was a very expensive proposition. And, cloud started bringing SaaS products along where that was no longer true. I could spin up a MySQL server. I knew how to run MySQL, but I could spin up a MySQL server and a Redshift server, which I did not know how to run, and not really have to worry about the maintenance of those outside of the how do you actually use it as a user. So we started to see this proliferation of outputs, right? So before, we were doing log processing, we were doing stuff in Hadoop, but stuff was kind of staying in Hadoop or going to our one data store, right? Like, you're doing a lot of work in, say, Hive or something like that, and then pushing out a much condensed version to something like MySQL for financial or something, depending on what you're doing. Whereas here it's like, I'll push some stuff to MySQL, push some other stuff to Redshift, I'll push some other stuff to, Arcade files to cloud storage just in case I need them later. And you start to see the introduction of things like pub subsystems, right? Stuff that's relatively difficult to maintain. And you start to see kind of an explosion in the number of different jobs you're running. And at the same time, we also saw some new processing models come along. It's kind of coincidental with the cloud stuff. One doesn't depend on the other. But at the same time, we also saw, the recognition that maybe MapReduce is not enough, right? Like, it's good. It's good for that like basic ETL application. But a lot of times you want to do more than one map and more than one reduce in the same pipeline. Because otherwise you have to, materialize things out to disk, and that gets slow. And now you kind of end up back in the beginning where you're hand rolling things like, okay, does this file exist yet? Yes, no, okay, I can run, et cetera, et cetera, et cetera. So things like Spark came along, that being, today the most popular, but at the time there were many of these, right? There was Cascading was another one. There was Crunch, which is interesting because Crunch is actually based on the exact same inspiration as Beam. They're both based on on Google's Flume project, which is not to be confused with Apache Flume, which also works with logs but does something different. Crunch is very explicitly Josh Wills left Google and missed Flume, so he wrote a new one. And Beam comes from that exact same place. So Crunch was another one. It's I think he got retired a couple of years ago. And then stuff that went along with that, like Apache Tez, and a few others that I'm probably forgetting right now. This is also the area where you started to see like alternate processing models like Storm and Samza come along as well. Although it's a little early for Storm and Samza. But that was interesting, right? Like this explosion of like different outputs, and then now choosing the data storage to be the best for what you were trying to do. So, what you want to do in Redshift is different than what you want to do in MySQL, and that started to become more feasible for business operations. So it kind of and as a result, we started moving the transform. We talk about ELT versus ETL these days. This was ETL, but it was like many different ETLs because you were transforming into different data stores. And then after that, I mentioned Samza, which comes from LinkedIn, but of course probably the most famous thing to come from LinkedIn in this era was Kafka. And Kafka changed a lot of things, to be honest, in the big data space because of the way it worked. So Kafka made it feasible to do streaming applications, I would argue. So, there had been message queue systems. The message bus was a popular thing for a while, actually, right around the time Hadoop came out. The enterprise message bus was going to be a thing. There have been message queuing systems like Rabbit and ZeroMQ, even Redis pops up at the time. But they all kind of shared a message-oriented flavor to them, which meant that anytime you were trying to do analytics processing or transactional processing in some sense, you had to keep track of every single message, right? Like, did I process this particular message? Yes, no. And that's actually, having to think about every single message is actually kind of an expensive proposition, right? You need some way of saying, like, this message but not that message, and in the case of redelivery, because any sort of streaming system, you're now in this kind of at least once world, right? And in batch, it's easy to think about at least once. It's like, all right, did it all work? Great, I can copy the files into place. But in streaming, it was much harder, because now, like, as a file level, you were now thinking about that at the message level. But Kafka brought the file level concept back, right? Because in Kafka, you really only had to think about partitions now. And you got to choose the number of partitions, and you could make that number, sizable enough. But you didn't have to think about individual messages. You just need to think about the partition and the offset, which let you conceptually treat it a lot like batch. And even today, batch, if you can do it, is going to be less expensive than streaming because there's just less to keep track of, and you can kind of favor throughput. But Kafka did that live. If you want to. Kafka's a lot of things, but one way to think about it is, it's a log with a cache strapped to it, where the caching strategy is the most recent stuff. And for a lot of real-time applications, that is probably the best caching strategy you can choose. And so what happened for practitioners like myself is we started moving actually a lot of our data processing that we had been doing kind of in the back end into the application layer now, right? Like, so we were now able to do what we did, right? These data heavy projects in more or less real time. Like Kafka, in a AWS zone or something like that has pretty good end-to-end latency, right? It's like in the double-digit milliseconds range, and so that let us start to build these little data processors that we put into operational stores. So some of those stores, from the last slide, started to move up into the application stack. We could have like Redis or Mongo or even Elasticsearch, stuff like that, up in the operational store and work on those. And then the batch system got relegated more to the data pile. Right? It wasn't a data lake yet. Like that implies like, I don't know, something that's kind of nice. This was just, where stuff ended up, and, legacy ETL started happening on it. And this ended up being kind of a microservices architecture. Later, that would get a little bit more formalized when stuff like K-streams kind of came out. We also saw this model being used less formally in other places like Storm and stuff like that, had kind of a similar model. And then, of course, when Kafka introduced like compacted or when they made it better to use compacted topics and things like that, we could actually start to do durable caching and things like that. So Kafka itself became one of the operational stores, and we could do like in-memory caching. That was super interesting. It also led to having to take on almost a more traditional software development practice, because now we're writing microservices. They need to be deployed, like you need the dark launch and A/B test them and all that kind of stuff. So we actually started learning a lot more about we had to deploy them like the application, and that was actually a big change, right? Like a batch system, it's really easy to think about upgrading your batch job, right? You just replace the jar and off you go. It's kind of the equivalent. It's like the difference between when you used to put software on a CD and ship it to stores, right? Like it's done now. Like you can't touch it anymore. That version is that version, versus modern SaaS products where it's like version doesn't really mean anything anymore. It's primarily we just choose them. and off we go. So now we're like actually the line between like a data science type of application and data engineer and application engineer is very blurry. Like where's my application in this graph? Where does my application really start? And where does my data processing end if if the application depends on the operational store now, right? And so now we have both batch and streaming as well. And then after that, into the bubble. So that's joining Google and YouTube, right? Where internally, Google has its famously its kind of own way of doing everything. It's been doing it for a very long time, and it happens in this case that internally and externally, Beam and Flume are very similar. There's some differences. Mostly things like language, right? Flume was written in C++ originally, but the programming model is very similar, and the data set size were much larger internally at YouTube. I was on trust and safety. Can't really talk much about what went on there, but suffice it to say, trust and safety is about looking at a lot of data all the time. And built, I was running one of the data engineering teams, and we had very deep pipelines, actually several very deep pipelines in these complicated graphs. And that's where like the Flume/Beam programming model was really starting to come into its own, right? Because it's great for these large graph structures and kind of understanding, putting them together, and then being able to run these day in, day out on massive data sets, especially joins. Right, joins in the MapReduce world were something you had to write a join by hand, and stuff like Hive came along and could do joins, but a lot of times, even with and when Spark came along, things got a little easier, but a lot of times you still have to hand write these, whereas in the view model, the join process is well understood and actually fairly efficient, so it's hard to beat it with hand-rolled MapReduce code. And all of that, is a history. So what did I learn from my experience? So I think one of the key things to take away is, in the industry, people talk about ETL, and now they're talking about ELT. It has gone back and forth several times over the years, right? It's all a matter of sort of cost, right? Like what is too expensive versus what is cheap. That's really what drives it. There's no right way to do it. It's what works best for the infrastructure you have available to you. Where best is usually, what can I do in the budget that I've got available? And where budget includes, the number of people. Certain things require more people, other things require more compute. And in reality, you always do them both, because there's no world, it's more like ETL, ETL, TTTTLT, right? It's like a huge combination of things. Nobody has just an ETL pipeline these days, especially these days. And kind of related to that, and also related to the compute to data, data to compute, grouping data, being able to organize it a little bit early on has huge operational impacts, right? Like the Kafka partition system is a good example of that. It is versus a message-based system. It was life-changing at the time. Now, of course, other systems, it's easier to deal with that, like PubSub at Google, right? That is really good at message-based systems now. But at the time, it was like, oh yeah, like this makes it feasible where it wasn't before. And finally, like the other thing, which I kind of didn't really mention with Kafka, that we also learned is, so once we started writing these little microservices versus these longer chains, we also noticed that we could, or gave us the freedom to start using other languages to write those microservices. Which, as ML started to come along, was super important. So when we started, of course, a lot of our services were in Java that we're talking to Kafka, because that's what the client library was. Although Kafka's client protocol is pretty simple, so it's not too hard to write a library. I've personally written one for Node. But it let us start to use other languages, which these days means if you want to use, for example, like TensorFlow, you probably want to get some Python in there. like using because that's what everybody else uses. So it lets people, and the people who know how to derive TensorFlow are comfortable with Python, and it let them start to participate in the process instead of kind of the old way would have been, researcher does their thing, builds their model, and then we port it to Java. I had that job of, okay, now we port it to Java for a while, and it's no fun for anybody. And also, it's a good place to introduce bugs, right? Like you built the model here, and there's a non-zero chance you're going to introduce some bugs doing the port, and the work in many scenarios. Sadly, you now have three problems where both implementations are wrong, but in different ways. You spend a lot of time trying to hunt that down. So that's that was the other thing we learned, and that's kind of this last bullet point, right? Which is, with Hadoop, we brought compute to data, and that was cool. We don't do that so much anymore because the cost benefit's not as much there. But one thing that newer systems are letting us do, Beam included, one of the reasons I decided to join Beam, is that you can now bring the library to data. I used to work with this guy named Daniel Bisson, and we were talking one time about why Java. This was in the Java 6 era, so that was a valid question. And his response was, well, that's what all the libraries are, right? Like anything I need to do, chances are there's a library for it in Java. And now, we can actually say, well, yes, there's a library for it in Java, but it may not be the greatest one. Now we can actually go out and start to pick the library that is the greatest. And I'm trained as a statistician, so I'm a heavy R user, or was. And that was one of the reasons, people would use R is like, well, the person who invented the technique wrote the R library for that. Like, even if it's buggy, at least it has their bugs in it, as opposed to someone else's bugs in it. So it'll at least match the paper. And that let us kind of take advantage of that. Also, like I mentioned, when you start moving to streaming, there's really no practical difference between streaming analytics and anyone developing a microservices architecture. And once you know that, you can start to treat it more like traditional software development, which feels slower. But traditional software development for microservices is like that for a reason, because you have different concerns, especially around things like trying to upgrade a service, right? Like microservices have to do this too. How do I do that? Things like Dataflow can do that for you, updating that. But it's not trivial to think about how you do that, especially if you have to change like schemas and stuff like that. And so adopting kind of that stance is often beneficial as a practitioner. And of course, the very most important one is that any organization of any size, even if it's just you, my first team that was doing Hadoop, I think there were 3 of us at our peak, working on the same team. You will have many pipelines, so it's definitely good to start thinking about not just your pipeline, but think about your entire organization's pipeline as one larger thing, especially when it comes to if you're trying to get something. And even if you start with one, you'll have more later, because if something's useful, other people will use it. And most interestingly, like in a lot of organizations, you run into 2 groups, both using similar stacks and similar technologies, that didn't know the other one was doing that. And so you actually have 2 completely disparate such pipelines that don't even know about each other and may have chosen very different paths for how they implement things. So keeping track of your pipelines is useful as well. So, and now the final step in the journey, or the current step in the journey, is putting, like I say, I'm putting my money where my mouth is, and join the Beam, we don't call it the Beam team internally, but the team that is primarily responsible for Beam at Google. So let's talk about Beam a little bit. Why did I do that? What do I think is interesting about Beam? So, having hung out in the Flume side a little while, one of the things is it made it a lot easier to build these complicated pipelines. Pipelines don't even have to have a single pipe. They can be multiple disjoint pipes that don't actually talk to each other, and that works and actually is often useful. Especially if you have something that has a large startup time, that's often where you pay a lot of your costs. So having multiple things happen at the same time in a single job is kind of nice. Especially on the batch side. On the streaming side, it gets a little bit more weird, right? Because now it's a lot hard. You don't necessarily want to do that. But so that was super interesting. The ability to combine languages as part, is a relatively new feature of Beam, but as part of the model is super cool, right? Because like I said, if you want to do TensorFlow or PyTorch or any of that sort of stuff, in PyTorch it's in the name, right? It's PyTorch. You're going to go over to Python to do that. And that might not be the best way to for example, read the data, right? Like, it might be that the driver for that in Python is not fantastic for some reason. You'd rather use the Java version to read the data and do the pre-processing, do your inference or model fitting in Python or R or something else, and then come back. And that's like super cool. And then it was nice to see the merging of the batch and streaming concepts. When you start doing a lot of data processing, especially stuff like windowing, right? Like, when you start doing a lot of data processing, you start to realize that there's always 3 timestamps you care about. There's the time the thing happened, there's the time when you knew about it, and then there was the time that you processed it. And those 3 numbers are different, and which one you want to use in your processing depends on what you're doing and depends on the mode you're doing it in. And being able to talk about that in the form of windows in the case of Beam is very useful, because it lets you kind of mentally merge your batch and streaming concepts. Because a lot of times, you saw this with the Lambda model way back when, right? Before Kafka, there was this concept of the Lambda model, which is you had like some not mostly reliable streaming stuff, and then you came in with batch stuff to fix it up later. That sort of thing still happens. Not necessarily because the streaming version is inaccurate, but for example, you change the streaming model. You want to go in and update your historical data to reflect that new schema or that new model. So you still end up doing all this stuff. There's an unanswered question. Pop it up. I'll get to the question in the end. Actually, I'm almost through that. And then, but like anything else, you wouldn't join. There's nothing to do if you're joining a team where everything is running great, right? Like, unless you want to retire. What do I think needs work? Well, it's really easy to make complicated pipelines, but unfortunately, making simple pipelines is just as hard as making complicated pipelines. So I think that's an area where things get rough. There is definitely a learning curve that folks go through to get there. And you could argue, yes, that learning curve exists in Spark and Flink and these other tools, but I think as an industry we can do better at that. The other thing that is a common problem, again, this is not Beam specific necessarily, I think is a common problem across the industry, is for any given stack, sharing components of pipelines, sharing transforms is hard. Some of that is a consequence of coming up in this like batch environment where the sharing model was basically libraries, right? Like, you would just have a library in your batch job because you're making this giant jar. But in streaming pipelines, that gets a little bit more weird, right? Like, and it might be interesting if you could separate your pipeline in different pieces, and now you can do what you do with microservices, right? Like feature flags and things like that. What if you could feature flag a part of a pipeline and replace it with a new pipeline, or use someone else's pipeline? Like I said, most organizations have many different pipelines now. And I would say probably a lot of the materialization that has to happen, which is probably the most expensive thing you can do in data processing, is because you need to share data between 2 organizations. And the only way to do that is through an explicit materialization set. Even though if they know about each other, right? Like, even though if you both knew about each other, you could totally write a pipeline that merged them all together. It would work just fine. But that kind of gets to the last point of things to work on, is like, when you start to merge pipelines together, now you have another problem, which is managing big pipelines is hard, right? Like when they start getting big and complicated, understanding their performance and how to improve it actually starts to get difficult because it's, you have to try to go in and look at individual stages and see what's happening. If there's a lot of interconnection, like if there's two things coming in, it's like, is that happening because of A or B and things like that? So like managing a large pipeline is fairly difficult. Again, I think it's a generally hard problem, but it is something that, I'm interested in thinking about. And then finally, what I think is exciting. So this is more, stuff that's happening right now, in case you weren't aware, because it's stuff that excites me and that I see it every day. So, to my first point about simple pipelines, complicated pipelines, there's been some really interesting work, in the Beam releases recently around things like data frame support, which, make it easier to write down a pipeline, particularly in Python. Because it's actually a very compatible model with the way Beam works, but also something that a lot of people understand, and it's kind of been like a structure that's becoming nicely formalized. So I think that offers kind of an interesting glimpse into ways we might explore making Beam a more accessible, more easily onboardable sort of tool. That a lot of people could understand without having to learn, essentially new programming. We also have what we call X-Lang, the cross-language stuff. I mean, that's really about, if you think about it, like cross-language is really about composing pipelines together. Today it's treated as a single pipeline, but really it's pipeline composition, right? Because now you're hopping between languages, so these are clearly different pipelines. I think that could lead us in a way of like shareable components and stuff like that. And I think that's super interesting. It also, I think, lets organizations work together more easily to solve problems as opposed to kind of throwing stuff over the wall of each other and having these very loose connections that themselves are operationally difficult to maintain. It's like, I can share two pipelines today. It's not that hard, right? And you have a pub sub that comes in, I have one pub sub that comes out, and then another pipeline reads from that. Like that totally would work. But now you have the operational overhead of making sure those pub subs are all working properly. And, what happens if one of them breaks, and how do you do batch over that, and that kind of thing. And then the last little thing that I find exciting is starting to see sort of application-specific efforts. So like machine learning has been one that we've talked about recently with the Beam Summit and stuff like that. To add different processing models, right? Like, people, when you're executing a model on a GPU, you're doing distributed computing. It just all happens to live in the same box. But if you go look at one of these like high-end boxes, there's a bunch of different GPUs in there. It's not just one. So it's like a little distributed computing environment inside your distributed computing environment that uses a very different processing model than the one we use, in the we're still in this kind of Beowulf cluster style situation. They're a little bit different, but largely, like if somebody came from the past, right, a time traveler came to the future and looked at a modern Google data center, they're like, oh yeah, it's a Beowulf cluster. I mean, the interconnects are a lot faster and the machines are a lot bigger and the cool rack hardware, but they're not like zip tied to grocery store shelves like we used to do, but they would recognize it for what it is. But the GPU models look more like those really old like HPC systems I used to work on. They're kind of like miniature versions of those. And modern HPC systems have a lot of those cards in them. So I think that's actually another sort of exciting area. But yeah, so that's kind of been my journey and kind of why what interests me about Beam and why it's not my day job.